This talk is about the change point problem. We're looking at a situation where the observations are high dimensional, and when the jump lies in a subset of the coordinates of these observations. So this is joint work with Farida and Nikiva. So I'll first start by recalling what the change point problem is, although we've seen that many times already. So I assume that I have a sequence of observations, and after some point there's a change point, and I look at this problem offline. So here I'm not looking at Q-sum test statistics, but rather at a retrospective change point test statistic. And I consider the change in mean problem. So I have a sequence of observations. There's a mean here, so say they are Gaussian, and then there's a jump at this change point location, and then the mean is shifted by some amount delta theta. So this problem was the focus of huge literature, and I won't try here to give a review of this literature. I just give here a few references. Now the question is, when you look at this problem in the asymptotics, so when you make the number of observations go to infinity, usually, as far as I know, most works consider the case where the dimension d is fixed. And the question is, what happens when the dimension is very high? Then a more meaningful setting would be to make the dimension grow the dimension grow as n tends to infinity. Okay, so to consider double asymptotic setting. So here's the problem. So assume that you have a sequence of observations. Again, they're Gaussian, and after some points, there's a change in mean, but only on a subset of the coordinates. Okay, so it's a regular change point problem, except that the change is occurring only on a subset of coordinates. Clearly, there's a difference between the setting where there's only the extreme case where only one coordinate jumps and all the other ones remain constant observed in noise. And the other extreme case is when all the coordinates jump at the same time. Okay, and this, what I call here the sparse alternative, is the case where a subset of coordinates jump, and it allows to interpolate between these two extreme settings. So to model this situation, we could consider a double asymptotics framework, which is actually inspired from by the literature in subset selection in regression, and namely, there's been lots of progress on variable selection in statistics recently in the last decades. The most well-known method is lasso, and also Danzig selector and all this. And so this asymptotic setting is very similar to all these works. So we make the dimension grow to infinity, and all throughout the talk, everything is going to be all the asymptotics are going to be tied to the asymptotic of d. Okay, so n tends to infinity, d tends to infinity, but everything is, the rates are parameterized by the rate at which d goes to infinity. And then the sparsity, which is the number of coordinates that jumps, is going to be some power of d. Okay, so keep in mind the simple setting where p is square root of d. Okay, and actually we'll see later that this is a place where we can observe a phase transition between two situations which are qualitatively very different. Okay.
Sorry, the change point occurs in each series at the same
time. Yes, at the same place. Yes. Okay. So the literature on this problem is very scarce, and actually I know very few works. One is the work by David Zygmunt, and actually I think you mentioned that in your first talk. although the modeling was different, so there was this geometric prior on the coordinates that allowed to model the sparsity. So here it's a harsher way to model the sparsity. We just assume that there's a subset of coordinate that jumps, and all the other ones do not jump. Another work which is related is the work by Jean-Philippe Vert and his co-authors. It's going to be a talk on Friday, and it's also the same setting, but actually Jean-Philippe will make will clarify the relationship with the variable selection. And there might be other works, but I'm not so aware of it. Okay, so what's the motivation for this? So there's a theoretical motivation, which I didn't mention here, and a real-world motivation. The theoretical motivation is actually very personal. So if you read the book of David Zygmunt on sequential analysis, when he considers the problem of the change point problem for multivariate observations, at some point he derives a formula for the boundary crossing probabilities when the dimension d is high for the limits. So consider some high-dimensional Brownian bridge, and you make the dimension d go to infinity. Then you see that qualitatively the limiting distribution is very different from what you would have expected. Actually, there's something going on. So that's the theoretical motivation. Clearly, it's interesting to see what happens when you make the dimension d go to infinity, not only for the asymptotics, but also for modeling. The real-world motivation is a multimedia indexation application. So assume that you have some TV shows and you want to index them. So you want to be able to retrieve the parts of these TV shows that correspond to this particular content. So say, for example, here it's a talk show, a French talk show that was very popular in the 80s. And at some point there's some interviews. Other parts it's uploads, other parts have music. And you assume that, so it's a very difficult modeling problem, obviously. So the way you treat it is basically you compute lots of what we call in machine learning features, so ways to describe what's going on in the signal. And it gives a very high dimensional signal, and you assume that the change is in mean. And some of the features are relevant for detecting change between this and that. Some features are relevant for detecting changes between this and that. Okay, therefore, it can be cast in the following framework. Another one is in biology and bioinformatics. Here I won't delve into details because I basically don't know anything about these applications. I just mentioned them for the sake of completeness. Okay, so here's the setting. So you have these observations. It's Gaussian observations observing noise, and we denote the jump by delta t. And the hypothesis testing problem is as follows. Under the null hypothesis, you assume that the jump is 0. Under the alternative hypothesis, you assume that the jump is larger than some threshold. And here we're going to derive minimax rates for this hypothesis testing problem. Basically, we're going to derive, depending on d beta, which is the power at which the sparsity, so p is equal to d at the power 1 minus beta. So it controls the sparsity of the jump. And tau, which is the location of the change point. This is what we call the detection boundary. And we're going to derive the detection boundary, which is the quantity for which the hypothesis testing problem makes sense. Okay, so for here we follow actually we use the tools of Yannick Barrault mainly. So there are many problems we can consider, and we first start with a very simple problem, which is the problem where we assume that we know the number of coordinates that jump, and we know the change point location. So this is just useful for the sake of deriving the lower bound on the minimax rate. And then the problem B, which is the actual problem we have in real life, we assume that we don't know the sparsity, and we don't know the change point location, and the hypothesis test should be able to be adaptive to the unknown sparsity and locate the change point. Okay? Oh, I forgot to mention. So here I'm only considering the hypothesis testing problem. So all the things I'm going to present also hold for the estimation problem, so the deriving confidence intervals for the change point location. But here I just want to detect whether there's a change point occurring in the segment or not. And I assume that there's at most one change point. Okay, so to describe the results, I need two notations. One is the type 1 error. Okay, so I'm going to write it as alpha. And the type 2 error, I'm going to write as beta. Okay, and for problem A, where everything is known, this is going to be beta A. And for the problem B, it's going to be beta B. And the question is, we want to find the conditions under which we can show that the sum of those two errors tends to 1. Okay, so for this, we consider a test statistic that is very common, which is this running maximum test statistic. So we write the mean, the empirical average on the left-hand side of a candidate change point, the empirical average on the right-hand side of the candidate change point, and we have this z quantity, and then we write the likelihood ratio. And if we know the subspace where the change point occurs, then we can write the test statistics as a projection of this z vector. Okay, so it's a multivariate quantity onto the subspace indexed by m, and m basically compresses all the information on this subspace. Basically, it's the list of the coordinates that jump. Okay, now it's time to think about the intuition on the problem. I mentioned these two extreme cases. One is when the change point occurs in one coordinate. The other one is when the change point occurs in all the coordinates. Okay, and actually these two extreme cases are the building blocks of the test statistic. So if all the coordinates jump, then it's actually a regular multivariate change point problem. And here we just consider a chi-square type test statistic. So it's just a Euclidean norm of this running maximum test statistic. And then we renormalize it by d and square root 2 of d. This is common. This you can derive by regular asymptotics. And this this test statistic, we're going to call it the linear test statistic. The other one is basically finding the subset of coordinates that jump. So it's a needle and a haystack problem. So, okay, so you have all these coordinates, and somewhere in the middle there is a subset of coordinates where a change point occurs, and you want to find them. How are you going to do that? You take your running maximum test statistic, you project it onto a candidate subspace, and then you max over all the test statistic to find the subspace that actually maximizes and seems to be the most likely place where a change point occurs. Okay? The question, so for this here, the threshold to calibrate the test statistic is quite straightforward. So this is classical statistics. For this one, it's actually a challenge because we need to know how to correctly renormalize our test statistic with respect to all possible cardinalities of the subset of coordinates that jumps, the sparsity, and all possible subset of coordinates. And it's actually a model selection problem. Okay, so here, the same way as David Zygmunt mentioned this BIC model selection penalty, here we have another kind of model selection penalty that actually arises in the threshold to calibrate the test statistic. So now, that's the take-home message of the talk. What we show is that if we want to perform well on all the range of beta controlling the sparsity, we actually need to blend these two test statistics into a combined test, and then we are adaptive to all possible values of the sparsity. Okay? We see that if beta is small, basically the number of coordinates where a change point occurs is small, then the scan test statistics, so this is the power, the scan test statistics performs bad. Conversely, if beta is large, then Okay, and whereas the linear test statistics performs well, and conversely, one performs well when the other one performs bad. And actually, they cross at the threshold, and the threshold is exactly p, the number of coordinates that jump, equal to square root of d. Okay, and here we observe a kind of phase transition between these two regimes. Okay, so the decision rule we propose is basically combining these two test statistics. So we basically take the one that fires, and this gives our decision rule for deciding whether a change point occurs or not. Okay, and actually, so these are just simulations. The picture I showed is actually corroborated by the simulation. We can see exactly the same phenomenon, and the transition zone is exactly at p equal to square root of d. Okay. Now, there are two questions. One is the statistical performance of this procedure. The other one is the computational efficiency of this procedure. If you want to find a needle in a haystack, the main issue is like, how would you find it? Okay, how much time will you take to find it? So you have to find in a set of d coordinates the p1s where a change point occurs. Okay, so if you think about it seems to be a computationally hard problem. Actually, it's much easier than it seems. If you take the running maximum test statistic and you sort them, then basically using a sorting procedure, which is linear, almost linear in the dimension, almost linear being that you have this term d log d, then basically if you can rewrite the scan test statistics in terms of sums of these sorted, it's basically all the statistics of the running maximum random variable. Okay, so basically, in other words, you can search through all possible subset of coordinates in a computationally efficient manner that is linear in time in a dimension, which is the best you can hope for. Okay. There's in the results I'm going to show, there's also another quantity that controls the rates. It's the location of the change point. So closer to the boundary, it's harder to detect the change point, but in the middle, it's much easier. So now I recall the two problems. I'm going to present the results. So first thing is to derive the lower bound. So if p is equal to d at the power of 1 minus beta, and we work in double asymptotics, then we can show that if these two conditions holds, so this is the separation boundary, this is the sample size, this is this function that basically controls the location of the change point. So if this quantity is negligible over as compared to square root of d, and if this quantity is bounded and is lower than 2 minus 1 over beta, then we can show that we can still detect the change point as d tends to infinity. Okay, so let's interpret this. Basically, okay, so I give a table later to summarize these results. So this gives us the worst. This tells us what is the worst setting in which we can work for and still hope to be able to detect the change points. So I just give some hints here on the lower bound, and maybe I don't have any time. So basically, the idea is to put some energy in the coordinates where a jump occurs in such a way that basically we can make the change point very difficult to detect. And for this, we use this prior on delta theta, which looks like Rademacher or random variables. And for the upper bound, which we're going to present here, we use deviation inequalities. So again, here we have these two conditions on P, D, the separation boundary, and the sample size, and this function of the location boundary. And we can show that the actual threshold that leads to, that allows our test statistic to work is actually, has actually this form. And actually, you can interpret this as a model selection penalty for our test statistic. Okay, So now the problem we wanted to solve in the first place was to derive a test statistic that is adaptive to the number of jumping components. And actually, we can show that our test statistics satisfies these conditions. So if we have these two additional assumptions, basically controlling, so this mean, yes. So they are a little bit harsher than the previous conditions, because we have, instead of log D, we have log D log N. And if we use this penalty, so note here that it's not exactly the same form as the one I presented before for the upper bound. So we have this combinatorial term which encompasses the combinatorial aspect of the scan test statistics, and it's basically depends on log of n, log of d, and log of p, okay, with the 2 in front of the log of p. And then we can show that the sum of two errors goes to 0 as d tends to infinity. Okay, so here I'm just going to summarize the results. So what are those results telling us? So basically, if we have modulus sparsity, basically we have d equal to d at the power 1 minus beta, but beta is smaller than 1/2. Then basically, if this quantity, so d at the power 1/2 minus beta, so this, let's forget about it, and the sample size, and this is the detection boundary. If this is equivalent, if this tends to 0, then basically there's no way we can detect anything. And if this this quantity tends to infinity, then we can show that our test statistics actually detects the change point. Okay. In high sparsity, when b is larger than 1/2, then everything is controlled by this AD squared, and we can show that if this threshold is smaller than square root of 2 beta minus 1, then detection is plainly impossible. And if it's larger than that, then we can show that detection is possible. And this is where our adaptive test statistic performs well. Okay, so here we can show the power of the test statistics as depending on the size of the jump renormalized by square root over p. And we can show that basically the power jumps to almost 1 at different thresholds depending on the size of this jump. And we see here that the difference between the high sparsity regime, where the power of the test is actually significant only when the size of the jump is much larger than square root of p, and the moderate sparsity, where basically it makes sense because moderate sparsity means that think of almost all the coordinates jump, and therefore this norm is very large. Then very quickly you get good performance. Okay, so this is a table to summarize all the results. So basically the take-home message is that if we're larger than this quantity, then we can show that this is the regime where our adaptive test statistics works well. And if we are lower than that, basically there's no way we can detect anything. Okay, I had one slide about the change point location. So we can also use these results to model the situation where the change point actually is very close to the boundary by making this tau over n go to 0 with some rates, and then we can basically control the performance of the test statistic. So in conclusion, so the goal was to study the change point problem in high dimensions, and assuming that the subset of coordinates had a change point, and the goal was to derive a test statistic that is adaptive to the unknown subset of coordinates where the change point occurs, and to show that the convergence rates of the test statistics are actually optimal up to a log factor. And this is what we showed. We can derive a similar approach for the estimation problem. So using a similar test statistic, we can derive a confidence interval for the change point location. And we can extend this work to the online version, so the sequential version where the observations income the system incrementally and derive a kind of Q-sum test statistic. And we're also studying extensions to inverse problem and time series. Thank you.
Why do you call it non-parametric? You're considering essentially a parametric model, right?
Yes, okay, so this was on purpose. So
Also, why chi-squared? You don't know sigma? In your model. In your
here I
normal
know
model,
sigma.
You do not know.
Yes, I know
That's
sigma.
why chi-squared.
No, I know sigma.
Ah, you know.
I know
Then why chi-squared?
What do you mean?
Why chi-squared statistic? Why do you need it? Chi-squared.
I assumed variance is 1 on all.
Do you know it in advance in your model? You have
Yes,
a
yes,
normal
I know.
model with no variance.
I know variance. Yes.
So why are you considering the chi-squared statistic as a decision statistic?
What do you mean? So what I call chi-square statistic.
Is not the optimal statistic is not the chi-squared.
Okay, so let's just be clear. So what I call chi-square statistic here is kind of abusive, but what I just mean is this is equivalent to a chi-square distribution with d degrees of freedom. That's all I mean. And
So why do you need it?
What do you mean by why?
You can use the likelihood ratio, right?
But that's exactly what I do.
Likelihood ratio.
Yeah.
It has a chi-square distribution.
Yes. That's exactly what I do. Yeah. But answering to your question, so what I mean by the non-parametrics, so usual way, the usual situations where we call things non-parametrics is basically where we have kernels and all these things. But here, so it's a situation where everything is linear and it's a parametric model, but still the rate is not 1 over square root of n. The rate is smaller, is slower than that. So we observe rates that are controlled by the dependence of d, n, and the sparsity. Okay, and in a way, it encompasses. It's part of non-parametric statistics. Okay, although the structures we are working with are all linear and the model is in a way parametric, but the rates they are not. I mean, they do not fall in the rates of classical parametric statistics.
I think that there is a large area of application of this problem in so-called panel data. So this is in econometrics. There is a number of papers connected with this situation, but this is the way that you have the time series.
Yes.
Time series, and you are considering the same problem. Usually, you don't consider there are in all, or just assume that there is a change point at the same time due to some activities. There are a number of results, and this is, I think that mostly what is used there is this kind of linear statistic because you don't.
Yes.
So that's, yeah, but the assumptions are quite general, and there are also results concerning the estimators.
Yes.
It's quite largely
Okay, I'd love to discuss that with you here. Yeah. Okay.
Can you do something when the z vector, when the vector of observations has correlation?
Okay. So. Yeah, sure.
The statistic that I suggested, I'm perfectly happy with when the coordinates are independent.
Yes.
Using projections like this gives me the idea that you could do something with correlated observations.
Yes.
It's not clear to me.
It's not clear to us either, at least from a theoretical point of view. But from a methodological point of view, clearly, what we see here. So, if you're familiar with lasso literature, what I do here is thresholding. Mm-hmm. This is hard thresholding. This is just applying the thresholding operator to the z vector. Now, if you think back, you can say, okay, when do I use this kind of thresholding IDs? So lasso is, for example, an example of this kind of IDs. So maybe you can derive a lasso kind test statistic, including the covariance here, and then apply some thresholding. So you would keep the computational tractability, but still have a procedure that captures not only the correlation and is consistent with some kind of some aspects of the likelihood theory. Now, what I don't know is what is the rate of that? How does it perform as compared to the best you can do? And so this I don't know. But clearly, you can some intuitions can allow you to derive some test statistics that hold for the correlated case. Yeah, so it's very interesting questions to pursue.
Let's put further questions to the break. Great. By the organizers. Thank you very much. Could we thank all the speaker and all of the other speakers?